So last time we were talking about orbit centralizer theorem, and we want to see its application and what kind of theorems we can prove. As I said, that it's one of the main central theorem, and there are a lot of interesting consequences of that. And one of the main applications we will see today. So let's just recall what we did last time: orbit stabilizer theorem. So, what is this theorem about? So, we begin with a group G group, finite group. So, G a group, which is finite. And a finite set. So, G is acting on A, which is a finite set, and G acting on A. So, this is what is given to us. Then, knowing the action, we can compute the size of A. There is a relation between size of A and the group G. That's what the theorem says, right? Then the first part, then size of A is nothing but sum of the size of orbits, where orbits come from representative classes of A mod G. Okay. So again, I will warn you or remind you or recall that what is the meaning of this sum. You have to be very careful when you are going to apply this formula in certain situations, because often we make mistake in doing this. So the formula here, what it means is that so the group. So let me just explain by the picture. So when group is acting on some set A, I have different orbits, right? So suppose I have this orbit of A1, and then I have orbit of A2, and so on, and some other orbit, let's say orbit of, and there are R orbits. Then as we saw in the proof, uh, this action gives these orbits, and these orbits are obviously disjoint, right? These orbits are disjoint because they come from some equivalence classes uh, uh, given by the action. So these are disjoint, and the size of A is sum of size of each orbit, right? So when we write down this equation here, and when we say that we are looking at size of orbit of A, you are supposed to choose one representative from each of these orbits, right? So one representative from here, and so on, one from here. Um, Often we make mistake when we are trying to compute the formula. We try to write down the orbit of each element of the set A, but then that will mean that we are counting this orbit like many times, right? And this orbit also many times, and then you will not get the right result. So you have to be very careful. First, determine the orbits and choose the representative of each orbit, and then apply the formula. You have to keep this in mind, right? I'm repeating this again because this is a potential place which we make mistake. The second part of the statement was that if I look at one orbit and want to compute its size, it can be computed by knowing the size of its stabilizer. So that is order of G by order of GA, where GA is stabilizer of A, right? Where GA is nothing but stabilizer of A, right? And hence we can rewrite the formula, the equation which is above. So this, let's say this equation was equation number 1. This equation 1 can be rewritten. This equation 1 can be rewritten. So thus 1 becomes size of A is equal to summation over representatives from each orbit, for which I am writing A mod G, and the size of orbit is now going to be size of order of G by order of GA. Okay, is this clear? This was the main theorem, orbit stabilizer theorem. there is a little exercise which I can leave it for you to do this, or we can do it later. And uh, is following that: suppose A and B are two elements in A which are in the same orbit under the action of G. All right. Then what can you say about GA and GB, the stabilizer of A and stabilizer of B? Then, uh, uh, then there exists G in G such that G times GA, G inverse is GB. Okay, I'll leave this exercise for you, or we can do it later when you can try yourself. It's quite easy exercise. In fact, the element G will come from the element which sends A to B. So, okay, so one of the very special situation where we are going to apply this theorem is when G acts on itself by conjugation. So we have seen that a group can act on itself in several ways, and one of the way which we considered earlier, uh, was left multiplication or right multiplication, which we call left regular action and right regular action, right? But now we are going to consider a different action of G on itself. So keep this in mind that a group can act on a set in more than one ways. Okay, so there is nothing unique about if you are given a group G and if you are given the set A, then mean that there is only one possible action. There could be more than one possible ways of defining the action, right? So so we are going to consider now conjugation action. So we are given the group G. So given group G, uh, it acts on itself as follows, right? So as I said that the group is given to me, and the set A is also going to be G, and the action is going to be as follows. So G cross G to, if you want to write it A here, I can do that also, not a problem. Let's write A so that it's easier to visualize. Where A is just G, right? So the action is defined as follows. So G comma A goes to G A G inverse. Okay. So this is called conjugation. So you can write this. So this is an action first of all. Let's check that. So this is an action. What are the things we need to check for an action? The identity doesn't change anything, right? So identity dot A. This is of course E inverse, which is simply A. So that is fine. Second property is that if I have G1 acting on G2 dot A, it should amount to first making G1 multiplying G1 G2 and then making it act on A, right? So let's verify this whether this is correct. We need to verify this equation, right? Okay, so how do we verify this? So let's calculate the left hand side, right? So left hand side is G1 dot G2 dot A. So by definition, G2 dot A, I will substitute this first here. So G2 A G2 inverse, right? Which is supposed to be an element of A. So now I can make G1 act on that, and that is going to be G1 G2 A G2 inverse G1 inverse, right? This is what happens. But the group multiplication is associative. And all this is happening inside the group G itself, right? So I can rewrite this as G1, G2, A, and then G2 inverse, G1 inverse. But this G2 inverse, G1 inverse is nothing but G1, G2 whole inverse, right? So G1, G2, A, G1, G2 whole inverse. And which is the right hand side, which is same as G1, G2 acting on the element A, which is right hand side. So this is an action. So it's quite clear that this is an action. Let's just write down this as a definition. Uh, so, so G group. Suppose I have two elements A and B in G. We say that A and B are conjugate in G if there exists some element G in G uh, such that GA G inverse is B. Okay, and this defines the relation on G, and it's an equivalence relation. And this equivalence relation is nothing but coming from this action, right? So I'd use that conjugation to define this action. You see that here. And the equivalence relation on A defined by this action is same as the conjugation action. Yeah. So I'm just trying to think of this in two different ways. Uh, One is that I can directly define on the group G what is the meaning of conjugation, and uh, remark conjugation on G is an equivalence relation. So I could have as well started just simply with this definition and check that this is an equivalence relation and then go ahead, right? But since I'm trying to think of everything from the action point of view, and I have already proved this orbit stabilizer theorem, so I want to think it from that perspective and derive the results using the theorem which we have proved earlier, right? Rather than doing the work again, we'll just apply that theorem here. So let's apply the theorem on. So we want to apply the orbit stabilizer theorem for conjugation action. Yeah, I hope this is not confusing. Within the group G, I can directly define what do we mean by conjugation. That what do we mean by two elements being conjugate, right? Uh, and the same thing I can interpret it as an action, right? And the action is, as I described earlier, that the G acts on itself. The set is also the G itself, and the action is given by G comma A going to G A G inverse. And if you do the calculation which we were doing last time, you will see that the orbits of this action are going to be equivalence classes which are given by conjugation. And these orbits are called, there is a special name to these orbits here, and these orbits are called conjugacy classes. Okay. The orbits here are called conjugacy classes. So orbit or equivalence classes, you can also say that this is also equivalence classes. Okay. I can write down directly the definition or here. So you can also say this as a definition that take an element A in G and conjugacy class of A, let's like the CLA is supposed to be all GA G inverse. This is called conjugacy class of A. in the group G, right? Why this is important? This is something beyond our course this time, but let me just write down a couple of sentences that why conjugacy classes are going to be very important in future or in general in maths. So why conjugacy classes are important. Uh, so they appear in representation theory. In particular, there is a very basic theorem or one of the first theorem you'll prove in representation theory of finite group is following. In particular, uh, the number for a finite group, let me write the precise statement. Of course, the proof of this statement is not for this course. This will be for representation theory course if you ever learn that. In particular, for a finite group, the number of irreducible uh, complex representations is equal to the number of conjugacy classes. Okay, so you will see that why this is important, because if you know conjugacy classes and how many conjugacy classes are there, that will tell you how many irreducible representations are there for that group G. So this is a very fundamental and important definition in some sense. This definition also something similar you have seen in linear algebra. So I like to point this out uh, and relate it to what you know already. So in linear algebra, we define um, uh, what do we call that? Suppose I have matrix A and I have matrix B. Let's say these are matrices in M and F. Uh, we say that A and B are um, equivalent if there exists P in GLN, is that PA P inverse is D. What is this called? What is this equivalence relation? This is called similarity. So instead of saying equivalent, I should say here similarity classes, right? This is what you I wanted to check if you remember this. So this is called similarity. So I should write down here the name. A and B are similar, right? And the whole theory of Jordan canonical form. Uh, this is the definition there. And uh, when f is equal to complex numbers, uh, and if I look at instead of MNF, we look at the only subset GLNF, right? Here we are trying to define similarity classes for any two matrices, including the matrices which might have determinant zero, right? But if you look at the subset where we look at only invertible matrices, then the similarity relation is nothing but the conjugacy relation, right? Conjugacy classes. So when F equal to C and G is GL and F, similarity, this is exactly same as conjugacy. And and the Jordan canonical form theory more generally Rational canonical form theory. Describes the conjugacy classes in GLN. So I'm telling you basically instance where you know already, you've already seen this phenomena. Yeah. So have you seen Jordan canonical form theory?
We skipped that last time.
In the linear algebra part two, the advanced linear algebra course,
Yeah, we skipped Jordan canonical forms. So
rational canonical form. Okay, you did not see the Jordan canonical form, rational canonical form theory. Okay.
yeah,
Uh, if you are going to do like group theory or advanced mathematics in future, this will be an important and useful topic. So you should try to learn yourself. It's very, very fundamental and important topic. Yeah. Uh, so maybe I don't know whether it was in linear algebra one part towards the end or no. Okay, anyway, let's not worry about it right now. But in general, this is an important topic, and this is part of the most of the linear algebra textbooks. And you should try to learn it yourself if you have not done it in the course. Uh, but I should have assumed that if you have done linear algebra 1 and 2, then it should have been covered somewhere. But anyway, uh, not a problem right now. Uh, but certainly you have heard of similarity and you know that kind of thing. So anyway, let's move on. I just tried to tell you that how things come together from different part of mathematics and something which you might have seen already. And it's sometimes important to realize this that all these things are so well connected to each other. Again, why it's important? Because in the representation theory it comes up that way, and we will see that it will also help us in achieving our goal. One of the goals, which is like learning about how much we can classify finite groups, let's say. Yeah. So let's get back to what we were trying to do. So we have defined a conjugacy class relation on the group G, and we want to apply orbit stabilizer theorem, right? So often this is what is called class equation, and almost every book will highlight this theorem, and it will tell you very important theorem, and they will give long proof. But you will see that the way we have built up the proof, it kind of is just one line proof. But let me write down the equation first. Okay. So G is a finite group. Then there is a formula. The formula is to calculate the size of G. And the formula says that order of G is order of center of G plus summation over order of G by order of the centralizer of elements in G, and this runs over those representatives where a, uh, a non-central conjugacy classes. Okay, let me explain this formula because that is more important. And once again, as I said, that there is always a chance to misunderstand this formula. I will repeat this again and again because this happens to a lot of people and a lot of students, and even like to experienced people it can happen because you often forget that over what this formula runs, right? Uh, so what is here? So let's see first whether we understand every term in this formula. Okay. So ZG is nothing but center of G, right? So Let's try to understand. Let's draw a line here, and then we are trying to understand the terminology here. So ZG is center of G. Why I have kept ZG separate? So if I take an element G, which is in the center of G, what is its what is conjugacy class of this element?
ZG, Z only,
What is Z?
Z of G, because
No.
it will
So
be
put again.
commuting with all the elements.
Compute again. What is so use the definition. You are not using the definition. So what is the conjugacy class of G? What is the definition? Definition will say that I have to compute all H G H inverse, where H varies over G, right? Now I know that G is in the center. So this implies that GH is HG for all H, right?
Simply G.
Yeah, so it will cancel out basically, right? And I'll get a single element G. Is that clear? Is this clear? I hope it's clear now. Just simply
Yes,
compute by definition. Nothing new we have done. Just follow the definition. So what is the meaning of center? Some element in center, that element commutes with every other element of the G, right? So when I try to compute conjugacy class of that element, it can't have any non-trivial conjugate because it commutes with everything. It has just itself. So what we have done here in this formula that all conjugacy classes of which size is a single element, size 1, they are clubbed together, right? An element is in the center. I mean, one can also write down this. I mean, I don't want to say it's a theorem, but it's a statement that some element G is in the center of G if and only if size of its conjugacy class is 1. Yeah, do you believe this?
Yes, sir.
We just proved it essentially. So if G is in the center, the conjugacy class size is 1 because we computed the size conjugacy class in fact, and the conjugacy class is the element itself. So conjugacy class size is 1. Every conjugacy class of an element will contain the element itself, certainly, right? Because there is always identity element to conjugate. So it always contains the element itself. So it has certainly at least size 1. What about center? Does center have non-trivial size? Or center can be trivial or center may not exist? What can happen?
Well, the center will always exist, right? Because you always
Can
have the identity.
can it be can it be like empty set? It cannot be empty set
It
because
cannot be
identity is
empty set.
always there, right? Identity is always there. It's a subgroup, in fact. It's a normal subgroup, in fact. You should verify all these kind of statements. It's a normal subgroup. It contains at least identity. Is it true that it is always bigger or center can be just trivial?
It can be just trivial. We could take SN,
Example. Okay, in symmetric
permutation
group, what
group.
is the center? Yeah, for
The
symmetric group, center is just
identity
trivial element,
permutation.
identity element, nothing else. And what is a group where the center is largest?
Any cyclic group?
Any abelian group, in fact.
Yeah.
So the largest center is for an abelian group where the center will be whole of the group. So let's write this statement also. I mean, just to remind you, center of G is whole of the G if and only if G is abelian. Yeah, these are kind of trivial statements, just restating the same statement in a way. But it's often useful to think of how different terminologies kind of interact with each other, right? So So it's important from that point of view. Okay. So we understand what the center is here in this equation here. Well, this is called class equation, and in the class equation here we have collected all those elements of which conjugacy class have single element, and that is nothing but the size of the center of the group. All right, and then as you have seen in the orbit stabilizer theorem, I have order of G by order of something, and this runs over non-trivial size basically. All those size where there is more than one, strictly more than one element, right? So this will always run over non-central conjugacy classes, where there will be conjugacy class size will be at least 2 or more than 2. So this formula has to be interpreted very carefully, and again, there are always chances of making mistakes. So keep this in mind. Let's try to prove this. Proof is kind of trivial from what we had done earlier. So we look at G acting on itself by conjugation, which we defined in the beginning, right? So G acting on G by conjugation. G, this we have checked that this is an action, and orbits are here conjugacy classes. Right? This is by definition, because what is an orbit here? Orbit is orbit of some element A is supposed to be all G dot A, right? Which is by definition here G inverse. So the G where is all G. And this is nothing but the conjugacy class of A. So there is a special name for these orbits, which is conjugacy class. So keep this in mind, right? The conjugacy class is basically nothing but the orbit of an element under the conjugacy axiom. It's just a new name for the same thing. Why this is so? Because this is quite an important concept which is used in representation theory and elsewhere. And what are the stabilizers of A, right? Stabilizer of A in G. What is that? So let's write down GA. That will be by definition G acting on A is just A, right? Set of all those G. Okay, let me write it more clearly. All those G in G such that G dot A is simply A. G dot A is nothing but G A G inverse, right? So what is this? Can you tell me?
Centralizer of A.
Centralizer of A. So this is supposed to be centralizer of A in G. Okay. So now we apply from orbit stabilizer theorem. Theorem part 2 implies that size of the set is same as G here. So size of G is summation over size of the group G divided by what? Stabilizers, right? Let me write that first. GA. And A runs over representatives. The set A mod G. And the set A mod G is conjugacy classes here. Now what we do here is that what happens if A is in the center? What will happen to this number, right? This is 1 if and only if A is in the center of G, right? Because centralizer is the whole of the group G.
Yes.
Right. I mean, I should have written one more line here. So this will become equal to summation over A in conjugacy classes, and order of G by order of centralizer of A in G, where this is nothing but representatives of conjugacy classes. So what we do is that we collect together all ones, and if I get one here in this computation, I will collect them together. How many one I get? That is going to be size of the center of G, right? For each central element, I will get one here, and then when I don't get one, then I have simply the formula this, where this is at least greater than 1. So this is non-central element. A running over non-central element. This clear? This proves the theorem. This proves the class equation basically. Let's try to apply this class equation and prove the theorem which I had written last time as an application. So the application, there are many applications, but one application will prove right away. And the theorem which we had written last time is let G be a group of order p square, where p is a prime, then G is a billion. Yeah, some people write a billion with small, but I try to write capital. In fact, it is isomorphic to either. So we have not defined what is the direct product, but in general, in fact, there are only two possibilities. G is isomorphic to Z mod P cross Z mod PZ, or Z mod P square Z. There are only two possibilities, and these are these two. But let's prove it is a billion first. So the application is this follows simply applying the class equation which you told just now. So I will apply the class equation for this group. The class equation for this group will say that order of G, order of center of G, plus summation over order of G by order of centralizer of A in G, right? And A non-central. To prove a billion, what do I need to prove in this equation? So I know I'm given that order of G is P square. This is given to me.
We should show that the other term is 0.
We need to show these terms here. These don't exist, right? This is what we need to prove, that they are not there, and the center is the whole thing. This is what we need to prove. Okay, we'll try that. So we have this equation that P square, order of G is P square. What can I say about this term here? So numerator is, so let's write this separately. So numerator is order of G by order of centralizer of A in G. Numerator, I know it is P square. Centralizer of A in G is always subgroup, right? And subgroup divides order of group G. So the centralizer order is either P or P square. And if it is supposed to be greater than 1, then whatever it is a multiple of P. Is this clear? This number, this is a multiple of P. Because numerator is P square, right? And this is supposed to be a fraction. which is divided by some order of subgroup. So order of subgroup divides order of group. Whatever this number comes out to be, this is supposed to be an integer, and it has to be a part of p square. So it has three possibilities: either 1, p, or p square. My claim is that it's not this. It's not this simply because if it was 1, then the centralizer of A and G is equal to G. That means A would have been in center, and we are assuming that this is not in center at the moment, right? So whatever that term is, P divides that term. Now, if you look at this equation, P divides the left hand side. P divides this left hand side because the order of group is P square, this thing here. P divides this term, hence P must divide the center. So first thing we prove that P divides center of G. This implies whatever the argument I gave implies that P divides the center of G. Is this clear?
Sir,
Yes, sir.
why will P divide the second summation?
Because the second
So,
summation is whatever is an integer.
hmm,
It, it's clearly it's an integer. We know because any subgroup divides order of the group, right? So it is supposed to be an integer.
yes, sir.
Okay. And all I have to say that it is not 1. Because order of group is p square. So the possibility for this integer, whatever is left here is, the part of p square. A part of p square could be just 1 p of p square, right?
Oh, okay, sir. Yes, yes.
I'm
Okay, got
using
it.
that our group has order p square. This is important, right? Obviously,
Yes,
otherwise
sir.
I can't conclude that. So I'm using that. Or I have to say that it is not 1.
Okay, sir.
And this will be not 1
So,
for any
may,
non-central element.
so
And hence it will be
basically, we are saying
fluffy.
that the order of the centralizer of A is either 1 or P. It cannot be P square.
Yes. For
Okay,
non-central
sir.
element, right? Non-central element.
Yes, sir. Yes, sir.
Otherwise, it has to be counted here.
Yes,
Okay.
sir. I got it. Thank you.
Yeah. So then this implies that P divides the center of G in that equation. Now, since P divides center of G is either P, order of center of G is either P or P square. P divides the order of center of G, so right? Yeah, this is correct. P center of G will be, it's a subgroup of G, and P divides it, so either it is P or whole P square. If center of G is P square, this means that center of G is whole of the G, and G is a billion, and we are done in this case. And we are done. We have to show that the other case cannot happen. Okay, so now let's assume. So now suppose order of center is P. So remember, uh, uh, we have center of G is a subgroup of G, right? And center of G obviously contains identity. In fact, this is of size P, this is size 1, this is size P, and this is size P square. We want to say that this situation cannot happen. This situation cannot happen, right? This is what we want to say. So let's say that I have some element G, which is in the group G, but it is not in the center of G. I can take the centralizer of this element, centralizer of G in G. And what can I say about the centralizer of G in G? This will certainly contain center of G, and it will contain properly. Why?
Because G will be in the center. So if they are
Because
equal,
G
then
will be contained in the centralizer and G not in the center, right?
right.
Because G belongs here, right? And G is not supposed to be in center by our assumption. So obviously this is supposed to be bigger. But centralizer is a subgroup. So what can I say about the size of centralizer of G in G?
Between P and P square, which is
This
not
is P
possible.
square, this is P, and it's not this, so it has to be the other one. But then this will imply that G is belongs to center, which is a contradiction. Which is a contradiction. Right? So that means this cannot happen. So the only possibility is that, hence, this proves the theorem basically. Hence, center of G has to be whole of the G. Proves the theorem. Very important, very interesting result. Right? Is it clear that how we applied the orbit stabilizer theorem uh, to get class equation, and a simple consequence of class equation is this theorem that every group of order p square is abelian. In fact, one can do a little more, that any such group will be either z mod p square z or z mod p cross z mod p. There are only two possibilities. This we can do a little later when we try to understand classification of uh, classification of abelian groups. Yeah, is this clear? Okay,
Yes, sir.
I'll stop here today. Next time, maybe next class, I will begin with what is called Silos theorem. And using Silos theorem, one can actually try to classify some more groups and get some more examples. Yeah, I uploaded an assignment, and those questions in those assignment are based on Silos theorem. So I will at least explain you Silos theorem and start proof of Silos theorem in the next lecture, so that you can start solving those exercises. Okay, any question?